let's learn about parallel circuits. A parallel circuit is one in which each resistor has its own branch. Now, sometimes you will see two resistors that occupy the same branch, but let's start with just a basic of having each resistor in its own branch, meaning each resistor is lined up in parallel with one another. In a parallel circuit, current travels through different branches before returning to the source. If you look at the diagram that's given to you there, you have three resistors, those squiggly lines. You also have a battery. Right? Again, remember the battery, the short side is the negative side, the long side is the positive side, that long line. So in this diagram, current, we follow electrons, is going to leave the top, travel up around that first corner, and then it gets to what we call a junction, where you see that resistor is connected to it. So at that junction, some of the current will decide to go through that first resistor. It'll come down to the bottom of the circuit, and it will go back around to the battery. If the current didn't go through that first resistor, it will go on and travel through the second resistor. If it doesn't go through the second resistor, it will go on and travel through the third resistor. But what you should understand here is that the current is only going through one resistor, right? So if you just pick one electron and follow it, it's only going through one resistor. So that means that all the energy it gained from the battery, it has to use all of that energy in that one resistor. So each branch must have the same potential difference drop. So in a parallel circuit, what happens if there's a break? Now hopefully when you did the FET simulation, you were able to get to this part of the activity and take a wire out. And if you took a wire out in the correct spot, what you should notice is that the other resistors, or in the case of the FET simulation, the other light bulbs continue to work. So this is an important thing about a parallel circuit. If there's a break in one branch, the current will still flow through the other branches. Very important. So here's a very complicated looking diagram. This is the same circuit that was on the other screen. However, I've added a bunch of other devices in here. Tons of ammeters and tons of voltmeters. So I want you to draw this so that you can refer back to it and follow where things are moving. Right? So pause the video, draw this in your notebook or on a separate sheet of paper that you can reference. It's going to help you. So what you have here is the battery. Around the battery on the left-hand side there, you have a voltmeter total. So that's going to read the total voltage of the battery. Electrons are going to leave the top side of that battery, the negative side, and go through ammeter total. So notice I've labeled it AT because all of the current has to go through there. Then the electrons are going to get to that junction, right, where it kind of makes a T. Some of the current will go through A1, down through resistor 1, and then back to the battery. If the current didn't go through A1, the rest of it's going to go through AY and get to another junction. Right? Some of the current will decide to go down through resistor 2, then through A2, and then it will go back to the battery. If the current didn't go through resistor 1 or 2, it will now go through A3, through resistor 3, and then back to the battery. So let's give these some values. If the total voltage of the source is 200 volts, okay, now this is a very large amount of voltage. It's just used so that we can look at the concepts here. You would never have something this large. But voltage of the source is 200 volts. The resistance of each resistor is also given to you. R1 is 100 ohms, R2 is 50 ohms, R3 is 250 ohms. Knowing that in a parallel circuit, Since the electron is only going through one resistor, it has to use all of its energy before it goes back to the battery. So since the voltage of the battery is 200 volts, the potential drop over each resistor will also be 200 volts. Okay. So we are going to analyze the other values in here. So what I want to find is the current that's going to travel through each ammeter that's in there. And to do that, we're going to use Ohm's law. Right? So remember, we use Ohm's law quite often. In this case, we're going to apply it to each individual resistor. So V1 equals I1 times R1. Now, in a parallel circuit, we know that the total voltage is going to equal the voltage over each branch. So I know V1 is 200. I know the resistance of R1, and I can solve for I. I get 2 amps. So I recommend that you pause the video, you try to do the same thing for resistor 2 and resistor 3. Determine how much current is going to travel through each branch. Okay, so hopefully you've done current through resistor 2. You should get 4 amps. Okay, that means if you look where resistor 2 is, connected to resistor 2, right after it, is A2. So 4 amps of current will also go through A2. And then resistor 3, you should get a current of 0.8 amps. That means 0.8 amps is going through ammeter 3. Okay, now, there are 2 other ammeters that I have in the diagram, A total and AY. So we need to figure out how much current is traveling through those. Here's a diagram where you can kind of see the path that the current is traveling. Right? So you have some arrows in there showing you where current is going. Notice current is only flowing in one direction. It doesn't go backwards. Right? So let's look at AY. Right? AY is up at the top, kind of in the middle of the circuit. And AY is going to measure the current that goes through A2 and A3. Right? So all of the current that goes through AY goes through it, gets to that junction, and then goes down through resistor 2 or continues through resistor 3. So if you add up A2 plus A3, you'll get the current that goes through AY, which would be 4.8 amps. Ammeter total, right, that first ammeter is going to measure the total current through the circuit. So if we add up all 3 branches, A1 plus A2 plus A3, that'll give us the total current of 6.8 amps. Now notice, when I calculated A total, I did not include the value of AY because that already includes A2 and A3. Right, so just be careful when you're analyzing. These are kind of like puzzles, and you have to figure out how much current is in each place and where you should be adding or subtracting things. So again, the total current would be the total current through branch 1 plus branch 2 plus branch 3. And that gives us 6.8 amps. So to find the total resistance, let's use Ohm's law to the circuit as a whole. So V total equals I total times R total. Total voltage I gave you as being 200 volts. We just determined that the total current would be the current through each branch added together, so 6.8 amps, and then I can solve for R total. Right, pause the video, pull out your calculators, make sure you get the same value that I did, 29.4 ohms. Now, here's a really important question. What do you notice about this resistance compared to the resistance that is in the circuit. If you look at the resistance of each resistor, you'll notice that those resistances are larger than the total value of 29.4. This is always true. Okay? The total resistance for a parallel circuit is less than any one of the resistors. I'm going to say that again because it's important. Circle this, highlight it, underline it. Make note of this. The total resistance for a parallel circuit is always less than any one of the resistors. This is because each path allows more current to flow because it's going to break up where it goes. So the total resistance for the circuit goes down. Okay. Here is actually how you can calculate the total resistance. Right? This is an equation. This looks different than all of the other relationships that we've looked at. This is the one that's a little bit harder. This is also on your reference table. Right? So 1 over the equivalent resistance of the circuit equals 1 over R1 plus 1 over R2 plus 1 over R3. If we apply this to our circuit, let's plug those numbers in. Right? Resistor 1 had a resistance of 100 ohms, resistor 2 was 50 ohms, and resistor 3 was 250 ohms. Okay. Again, I recommend that you pause the video, try to do this calculation on your own, and then check your work. So when you simply just divide these, right, here's what you get. Add them together, but notice that this is 1 over the equivalent resistance. I need to calculate the equivalent resistance. So I'm going to take the inverse of 0.034, which gives me an equivalent resistance of 29.4 ohms, which is exactly what we got when we calculated it using Ohm's law. Okay. Now, the thing with parallel circuits, I'm going to go back a slide real fast. Right? When we talked about this total resistance being less than the smallest resistor, when you have resistors in parallel, it allows more current to flow. Okay, now, a really great analogy is to think about when you get on or off a highway and you have to go through a toll booth. Okay? If there's one toll booth open, all of the cars have to merge, line up, wait their turn, right? Traffic slows way down. If they open up a second toll booth in parallel, right next to the first one, then the cars have a choice of which toll booth they can choose. If they open a third one in parallel right next to it, now there's even more options. So traffic will continue to flow much faster through those toll booths. Similar thing can be thought about when you think about parallel circuits. Right? The more branches you have in parallel, the faster the current will travel through there. Right? And the faster the current travels means the value of the current is going to increase. That's a really good analogy to use when you are analyzing parallel circuits.